Namaskara. We will continue our discussions on the algorithms for all pair shortest path problems. We have seen that using the idea of k-paths, we could arrive at an algorithm with complexity order n cube. The algorithm was designed by Floyd and Warshall, and whether the graph is sparse or dense, the complexity is always order n cube. If the graph has got less number of edges, is it possible to arrive at a more efficient solution than n cube? Okay, that was answered positively by Johnson, and we are going to take a closer look at Johnson's algorithm. It's a very clever algorithm. It's using the existing resources in a very clever way. We know that the Dijkstra's algorithm can be used only for the graph that has got positive edge weights. N times Dijkstra's algorithm's application will be more efficient. However, we need to have all the edge weights to be positive. How do we achieve that? Johnson's algorithm makes some clever moves towards it and arrives at an efficient solution for sparse graphs. The algorithm by Johnson runs in order n square log n nm time. So look at this expression n square log n nm. M is the number of edges. If m is order n, then this becomes n square log n algorithm. If m is something like that, like n, or even if m is something like n log n, in both cases the complexity becomes order n square log n. So for graphs with less number of edges, order n square log n is more efficient than order n cube algorithm. So Johnson's algorithm will be more efficient if the graph is sparse. If the graph is dense, it has got a matching complexity. If m equal to n square, which is the property of a dense graph, the complexity will be n cube anyway. So in the worst case, it just matches with Floyd-Warshall's algorithm, but if it is sparse, it turns out to be significantly more efficient. Okay. So first let us make one simple observation. Suppose all edge weights are positive. If all edge weights are positive, simply apply Dijkstra's algorithm n times, starting from each vertex as a source vertex, apply it as n times. We have an implementation of Dijkstra's algorithm with complexity n log n plus m. When you apply n times, the complexity will be O n square log n nm. This is the promised complexity of Johnson's algorithm. Okay. Therefore, if all edge weights are positive, we don't have to do anything, simply apply Dijkstra's algorithm n times and you have n square log n plus nm algorithm. But what if the graph is a mix of positive and negative weights? Of course, we still want the graph to have no negative cycles, no zero cycles, but it may have a mix of positive and negative edges. If that is the case, we simply cannot apply Dijkstra's algorithm. Dijkstra's algorithm does not work if edge weights have a mix of positive and negative weights. Therefore, we have to use the only known algorithm that we have seen so far, Bellman and Ford algorithm. But Bellman and Ford algorithm, which is capable of handling mix of positive and negative weights, runs in nm time. So n times nm, if you apply Bellman and Ford n time, then the complexity will be n square m, and when m is n square times n square, it can go as high as n power 4. Therefore, applying n times the Bellman and Ford is not a good idea. Okay? But Bellman and Ford is capable of handling positive and negative weights. Therefore, how do we improve the complexity of n power 4? Here is the technique. This is called the transformation technique. It is very popular in mathematics. If a problem is hard to solve in one domain, they transform it into another domain and then they solve it easily in the transformed domain. So often mathematicians will try to find an equivalent way of doing the same thing, but in a more efficient manner. You call that as a shortcut, you call that as an alternative way of doing, and so on. But in computer science we value such ideas because these alternate methods sometimes could be computationally very efficient. So transformation is a very powerful and an interesting idea, very popular in mathematics. We are using that in computer science. Here is a very good instance of that. We are going to transform the weights. Let us assume that h is a function and we transform the weight in the following way. W dash uv is wuv plus h of u minus h of v. So where h is just an arbitrary function. H is a function from v to integers. Okay? Just let us assume that we have transformed the weights. I am not changing the graph, I am only changing the weights. Now, if I take an arbitrary function h and define w dash transformed in this way, the w dash has got the following interesting properties. P is a shortest path from I to j under w if it is a shortest path under w dash. That means you can find the shortest path by working with w dash. The same path can be used. Only the path. The weights will vary, we will see that in a moment. In other words, I can solve the shortest path problem by taking the weight as w dash. Whatever the path I get, I can take the same physical path as a shortest path under w as well. For any cycle c, wc is w dash c. Therefore, if the graph has got no negative cycle or no zero cycle under w, then even under w dash it will not have any negative cycles, it will not have any zero cycle, because the costs of the cycle are preserved by this transformation. Very easy to see. Simply add all the weights, the h values will cancel out and you can see that the telescopic sum is identical. WC is. How are the weights of the paths related? The weights of the path are related like this. WP is W dash P plus Hj minus Hi. It is depending on only I and j. H value of I and H value of j is known. So after finding the path, we will have the weight of the path under W dash. What we have to do is that we take the weight under W dash, add H of j, subtract H of I, you are getting the weight of the same path under W. Therefore, after finding the shortest path under weights under W dash, we do not change the path, but we can change the weight by this simple operation, very simple operation. We get the weights. Therefore, I am going to solve the problem of all pair shortest path under W by solving the problem under W dash and then come back with respect to W. This route I would take, and this is much more efficient way to solve than directly working with W. We will see why going from W to W dash and working on W dash and coming back from W dash to W is more efficient than working directly with W. We have seen already, if you work with W directly, the only way is you have to apply n times the Bellman and Ford, and that is n power 4. Therefore, working directly with W is not a good idea, all right. So what we do is, we are going to find a H in such a way that W dash is positive, okay. W dash is positive for all edges. The transformation is done. So W is a mix of positive and negative values, but W dash is always positive. There is an advantage in working with W dash that is positive. You can apply Dijkstra's algorithm n times and get this complexity. Therefore, all we have to do is that make sure that in the transformation we go from W to W dash, and W dash has got all weights to be positive, okay. So here is a trick how to find that H. The trick is use Bellman and Ford algorithm once to find a H. We have to find a H. We are going to use Bellman and Ford algorithm once to find a H. Then use a H to transform W to W dash. Then work on W dash. Only Dijkstra's algorithm I will apply on W dash, okay. So this is the outline of the algorithm. So the algorithm at high level is this: use Bellman and Ford algorithm to determine a function such that W dash is positive, these values are positive. Solve all pair shortest path problem by using Dijkstra's algorithm n times on G with weight function W dash. Because W dash is positive, you can apply Dijkstra's algorithm and apply this. Let D dash be the shortest path weight matrix obtained. Then how do you construct the matrix D? Matrix D is the shortest path weights under W. This is the way to go from W dash to W. We have seen that already, right? And return D. Construct this. What is the total complexity? The total complexity is order Mn. This is for Bellman. Bellman and Ford algorithm you are applying once, Mn time. N square. N square is for constructing W dash from W and constructing delta from delta dash. They take n square plus n square. I can add another n square. Actually, it is order n square. It is just 2n square. And a single use or application of Dijkstra's algorithm takes n log n plus m time. This is single application. N times Dijkstra, when you use, it becomes n square log n plus n m, and that is what is written here. This is the cost of n application of Dijkstra's algorithm. So n square log n n m. So n square log n plus n m is the dominating term. Therefore, this sum has a total complexity given by O n square log n plus n m. Okay? This is Johnson's algorithm. All we have to now do to complete our discussion is how we are building the H function, okay? Because Once we know how to get the H function, all things are done as discussed, and we have an n square log n plus nm algorithm in our hand. So it remains to discuss on the construction of H. How do we construct the H function? Now if the graph, whatever is the graph, this is G, I am going to add a vertex S, a new vertex S, and connect that vertex S with every vertex of the original graph. So this graph is called G dash. So if G has n vertices, G dash has got n plus 1 vertices. One more vertex is added, okay, and I am going to add n edges. From S, all vertex of G is connected, and I give a weight 0 for the newly added edges. The weight is going to be 0, okay. Now solve the single source shortest path problem on G dash. G dash is still working with the weight function W. I have not done the transformation. G dash has got the weight function W, and new edges that are added, they have weight 0. Now solve the single source shortest path problem using Bellman and Ford. Only Bellman and Ford can be used now, and when you use that, you are going to get the shortest path distance from S to all vertices, okay. Let us say this is an edge UV, this is U, this is V, this is an edge UV. So I have, because I have used the Bellman and Ford, I have delta U computed, I have delta V computed. If G has no negative cycle, G dash has no negative cycles, because in G dash I have added a vertex and then added only the 0 weight edges. They are all one way edges, okay. These are all one way edges. No new cycle or nothing is created by this, okay. They are one way edges and their weights are 0. Therefore, this is not introducing any new cycle. The same cycle in G is what is there in G dash as well, and they are all positive, non-zero. So I can apply the Bellman and Ford algorithm and get delta U and delta V for all vertices. Of course, delta S is 0, delta S is 0, but that does not matter, we are not interested in that value. Look at delta U and delta V. What is the property of this delta U and delta V? So if you take any edge, the delta U and delta V, because we are considering the graph in which vertex set V is 1 to n. So let me write vertex I, vertex j, delta I, delta j. The delta I and delta j, they have a special property, this we know, this is the Bellman's inequality, right. So by moving delta j to the other side, you immediately see that Wij plus delta I minus delta j is positive. Therefore, all I have to do is define a function h of I to be equal to delta I. This function if I use, and if I design my delta, if I define my W dash as Wij plus Hi minus Hj, it is guaranteed to be positive. It is guaranteed to be positive. And that is it. We have completed our discussions on the algorithm. Therefore, to summarize, all we have to do is that when a graph is given, add a vertex, draw edges with weight 0, solve the Bellman and Ford algorithm, and for each vertex I you would have got delta I, set h of I equal to delta I, define a new weight function W dash using this formula, define a weight function W dash Ij using this formula, W dash Ij is guaranteed to be positive, apply n times the Dijkstra's algorithm and solve the problem. Okay. This completes the discussions. And as a final remark, if the original graph has got any negative cycle, that can be detected by Bellman and Ford algorithm. In G dash also the same negative cycle will continue to exist. Since we are running Bellman and Ford algorithm on G dash, we would have detected that negative cycle and we can exit there itself without any further work. If the graph has got no negative cycle or zero cycle, we proceed further with the transformation and solve the problem efficiently. This completes our discussions on Bellman and this completes our discussions on Johnson's algorithm. In our next session, we will begin our discussions on minimum spanning tree. Thank you.